Hello, folks. This is Mr. Kim again. All right. I'm recording this video for your independent session work assignment number 10. Uh, you'll so I'll give you the instruction regarding this assignment number 10. Yeah. All right. So your assignment number 10 is going to be on handout number 5, limits of trigonometric functions on analytical approach. I'll post this assignment as soon as I'm done with this recording. So the instruction is watch this lecture video on handout number 5, limits of trigonometric functions, and take notes, please, either on a separate piece of paper or printed version. And then you're going to take a picture of your notes and submit it to get the full credit for this guy. Yeah? And not only for the credit, but you need this so that on Tuesday when I continue these notes, you know what I'm talking about. Yeah? All right. So make sure you download this for the assignment and then start working. Right? Okay, so let's see. So it will look something like this. Handout number 5, limits of trigonometric function and analytical approach. It's not entirely a new idea working with this problem here. Only thing is, it's going to be, why is it doing this? Okay. We're just dealing with tricks. Okay, those of you who are not comfortable with tricks, you might want to revisit those concepts either using Khan Academy or I told you I'll share that mini lesson video on tricks, so you can watch that too. It's not available yet, but I'll make it over the weekend. So we have already looked at how to evaluate limits of trig functions by direct substitution, right? So those are those two cases. However, there will be cases where you'll get 0 over 0 indeterminate form, and then you might have to use some different technique to find the value, just like you're dealing with algebraic functions. Yeah? So let's take a look at this one. Let's jump to it. So here, the limit of this guy as theta approaches 2 pi over 3. Do a direct substitution here. Then you get sine of 3 times 2 pi over 3 over 3 times 2 pi over 3, which is simplified into sine of 2 pi over 2 pi, right? You see those 1 over 1, right? 1 over 1, so simplify there. We can further simplify it because we know sine of 2 pi. How do you find the sine of 2 pi? So that unit circle, right? X and Y. Then you say 0. And then let's see, pi over 2, which is 90 degree, pi 180, 3 pi over 2, 270, and then 2 pi here. All right, and then let's draw a unit circle here, where the radius is equal to 1, right? Okay, sine of 2 pi, so where is that located? So that means I start at this coordinate, which is 1 and 0, x value being 1 and 0. And then you go around as much as 2 pi, right? Which is 360. So you end up here. So you have to know that from unit circle, the x value is corresponding to, x coordinate is corresponding to cosine of that angular rotation, and y is corresponding to sine of the angular rotation. So right now we're talking about sine, right? So we're talking about the y coordinate, which is equal to 0. So sine of 2 pi will be equal to 0. So you have 0 over 2 pi, which is equal to 0. All right, so we have a nice defined value just using a direct substitution. Simple as that. Same thing here. If you use a direct substitution, 2 times cosine of pi, but you're squaring that, right? And then what you're going to have is, then we need to find what the cosine of pi is. Where's cosine of pi going to be? Let me use a different pen here. So I start here, and then pi is 180 degrees, so this is how much rotation it happened, right? So we stop at pi here. So we take a look at the coordinate here. That will be -1 and 0, yeah? So when we have -1 and 0, cosine has to do with x coordinates. So we're talking about this guy here, right? -1. So cosine of pi is actually going to be -1. So all you gotta do is 2 times -1 square, 2 times 1, so you get a nice real number value 2. Oh. We just hope that all the limit value graphs or evaluating limit problems, just you can solve it with a direct substitution just like that, right? However, these are actually the rare cases where it works out really fine. This only happens because each of the function above was defined at the value that data was approaching. Okay, the value that data was. However, we have seen that even in the algebraic world, not all functions are. There's a typo there. Not all functions are defined at a value, but still their limits exist. Right? There are those cases that you have seen. Same is true in this trigonometric world. Okay, so what do we do in those cases? But first of all, let's take a look at this guy here, evaluating the limit of this guy. So let's consider for a moment the limit below. Try evaluating this limit by direct substitution. You do a direct substitution here, then you have 1 minus cosine of 0 over sine of 0, but you're squaring that value, right? So that means we need to find what cosine of 0 and sine of 0 is. If you go back up there, sine of 0 means no rotation happens, so we're talking about this point here, right? So what's cosine of 0 is going to be 1, which is the x coordinate of that point. And sine of 0 is going to be just simply 0. So here you're going to do 1 minus 1 over 0 squared, which gives you 0 over 0. So it looks like our function here is undefined when theta is equal to 0. So this is indeterminate form, right? So what do we do when we run into this problem? So you might think, oh, can I factor things out? Ooh, I could do sine times sine, but does it help? Not quite. Can I do rationalization or conjugate? Actually, conjugate process works here. I actually prefer that method. But since it takes a little bit more time to understand that method, we're going to use a different method. And that involves, in this case, using trig identities. Okay. So what is trig identities? So today we're just going to look at simple trig identity. So I know not a lot of you folks have enough exposure to trig from last year due to distance learning, thanks to COVID-19, right? But I'm assuming you folks are comfortable with this when we're going over this problem. And those of you who are not, it's fine. Just follow along. I don't know why I drew this, but let's try doing this. Okay, your trig identity. Very simple one that you just have to know is the sine square of theta plus cosine square of theta is equal to 1. And that actually is proved using Pythagorean theorem. But that I will not go over in this particular lesson. I will go over that in lesson that the mini lessons that I'm going to post on trigs. Yeah. Well, assume this is true for now. Sine squared plus cosine squared is equal to 1. And there's a lot of other trig identities that are derived from here, but I'm not going to go over it because we don't need that right now. And also another thing that you folks have to know is the fact that tangent of theta is equal to sine over cosine. Okay, sine theta over cosine theta. That's the definition. And there's something like cosecant of theta, right? That you know it as 1 over sine of theta. Is a reciprocal, so cosecant is reciprocal of sine. And then another thing is secant theta. Secant theta is 1 over cosine of theta. This is sufficient for today's lesson, and I'll introduce you more trig identity as we go along, because I don't want to overwhelm you at this point in time. Yeah. All right, so let's go back to this problem. This will actually help us out. Trig identity will help us out simplify this equation so that we can find the limit value. Okay, so what do we do here? I can rewrite limit of 1 minus cosine of theta over sine square of theta using a trig identity, and way to do that is follow along. I know that this is the most important part here. Sine square plus cosine square gives me 1, right? Doesn't matter what theta value is. Sine squared theta plus cosine squared theta always gives me 1, no matter what, as long as those angles are same angle. So I can actually derive this. So if I want to find sine of square, so how can I represent sine of square theta differently is I can rewrite this as sine of square theta is equal to 1 minus cosine square theta. Because we know those two things add up to 1. That means if I want to find the sine square, I just have to subtract this guy from 1, right? Which is cosine square, right? So I can rewrite this as limit of 1 minus cosine of theta over 1 minus cosine squared theta as theta approaches 0. Where do we go from here? Now another manipulation is required. You'll see this guy and see that kind of looks similar to a squared minus b squared, right? Do you see 1 square minus cosine square, right? And you know how you can factor this out as a minus b times a plus b. So maybe we'll be able to use that, right? Just because you have cosine square, don't get scared. It's just same thing as this, right? Like example would be 1 minus x squared can be factored out into 1 minus x times 1 plus x. That x happened to be cosine of theta in here. So it's same thing, just a little longer, right? Then you can rewrite as a limit of 1 minus cosine of theta over 1 minus cosine squared theta can be rewritten as 1 minus cosine of theta times 1 plus cosine of theta. Theta approaches 0. So this whole thing, when you multiply these two factors, you will get 1 minus cosine squared of theta. Oh, and how is this going to help us out? You'll see that this is 1 minus cosine of theta, but that's 1 minus cosine of theta. So you can simplify it as 1 over 1. Then I'm left with this simplified function 1 over 1 plus cosine of theta as theta approaches 0. We do a direct substitution here, and you will get a nice number now. 1 over 1 plus cosine of 0. And we established that cosine of 0 is actually 1. Right, again, going back to that unit circle. Yeah. And then there'll be 1 over 1 plus 1, which gives you 1 over 2. Ain't that nice? So we're saying, even though this function 1 minus cosine theta over sine squared theta is undefined when theta is equal to 0, a limit, when you find limit of this function as theta approaches 0, it will approach 1 over 2. And we have to use trig identity in this case and some factoring to cancel things out here or simplify it. Just to give you a little bit more context here using the what do you want to call it? Graph. So this is the graph of the function that we're talking, 1 minus cosine theta over sine square of theta, or sine theta, but then you're squaring that. And so you have this recurring pattern here, right, in the graph. But we're interested in what happens as this function is approaching theta equals to 0. So it looks like it's approaching like 0.5, which we got it, right, 1 over 2. But you'll see that when I actually click on 0, do this for me, please. I'm not talking to you folks. I'm talking to my mouse. Okay, let's see. Close. 0. Okay. Ooh, finally. Okay. Do you folks see that? It says 0 is undefined, right? If you look at that. So there's no actual value of this function when x is equal, or theta is equal to 0. One thing I don't like about decimals is that they don't have a hole here, but you're supposed to have a hole over there to signify that it's not defined there. But limits, if you look at it, it's approaching 0.5 from the left-hand side, and then it's approaching 0.5 or 1 over 2 from right-hand side. So we know the limit, graphically speaking, too, is approaching 0.5 or 1 over 2. But we proved it using analytical way, right? Okay, let's do a little bit more practice with this people. So find each of the following limits by rewriting the function in a form that is defined for the approach value of theta. I want to tell you before we proceed, it is important to note that in all cases of evaluating limits, direct substitution, right? Direct substitution should always be tried first. Okay. And then you might get 0 over 0, you might get 5 over 0, then maybe you have vertical asymptote there, right? And then you work it out. Yeah, so if direct substitution does not yield the value, then you go into simplification if you can work it out. And it doesn't always work out, just to give you heads up. But in the cases when it works out, you can actually find that limit value, which is pretty awesome feeling, right? Okay. So here, let's try it. Limit of 3 times tangent theta times cosine theta as theta goes to 3 pi over 2. So if you do direct substitution, we're looking at this. Limit of 3 times tangent of 3 pi over 2 times cosine of 3 pi over 2. Right? Oh, let me erase that limit part actually, because we did the direct substitution right now. And then what do we get? So we need to figure out, again, let me draw, let me actually widen this. All right, let me draw the unit circle there, right? Pi over 2, pi, 3 pi over 2, which is 270 degree, and then 2 pi. And then we know this is 1, 0, 0, 1, negative 1, 0, and then this would be 1, 0, and negative 1. Okay. So right now we're talking about 3 pi over 2, right? So we're saying it goes past pi, but then it stops here. So we're talking about this particular point, coordinate is 0 and negative 1 in unit circle. That means our, remember x has to do with cosine, and then y has to do with sine, right? And then also we said tangent is actually sine over cosine. So it would be actually equal to y over x. Okay. Okay, so first of all, let's try to find tangent value. And tangent value of 3 pi over 2 will be sine of 3 pi over 2 over cosine of 3 pi over 2, right? Which will give you sine of 3 pi over 2 will be the y value, so that will be -1. Cosine will be 0, so you have a 3 times -1 over 0, right? It is already defined, we can see that. How about cosine of 3 pi over 2? We established that's 0, so you have a 0 over there. So you have a case where this is like, 3 times -1 times 0, so you have a 0 over 0 case here. Right? So direct substitution doesn't really work for this case. But at least we know that we can probably work this thing out using the technique that we used up there to simplify the function and possibly get a limit value. So how do we do that? So this is what I will do. First of all, I know tangent, we already wrote it down, is equal to sine over cosine, right? So that actually helps me out. I mean, we actually wrote that down over here too. Tangent is sine over cosine. So why don't I write down that whole equation into this? That limit of 3 times sine of theta over cosine of theta times cosine of theta as theta approaches 3 pi over 2. And some of you folks already see it, huh? That's cosine of theta over cosine of theta. So you're like, ooh, you can simplify that, assuming that theta is not actually equal to 3 pi over 2. We're just approaching it. Then I can simplify that into 3 times sine of theta, because cosine over cosine is equal to 1. So now, right now, I have a limit of 3 times sine of theta as theta approaches 3 pi over 2. Do a direct substitution here, then you get 3 times sine of 3 pi over 2. And what was sine of 3 pi over 2? That's 3 pi over 2, and then you have to look at the y-coordinate. That should be -1. So that would be 3 times -1, so it would be -3. Pretty nice, right? So even though our function 3 times tangent theta over theta times cosine theta is not defined at theta equals 3 pi over 2, we can see that the function is approaching -3 at that hole right there. Okay. Let's try the next one. Third one, I want you to try it on your own. It's very similar to what we did over here, so you can try it on your own and then check the answer with me on Tuesday when we continue this lesson. But yeah, check this out. So limit of secant theta times cosine theta over 4 theta. So we established that secant of theta is, it's over here. I don't have to rewrite it. Secant of theta is 1 over cosine theta. So if you do a direct substitution here, let's see. Secant of theta gives you 1 over cosine theta. So you get secant of pi over 2 times cosine of pi over 2 over 4 times pi over 2, right? And secant of then pi over 2 be the same thing as 1 over cosine of pi over 2, right? Which means we need to go to pi over 2, which is 90-degree rotation. This time is we stop here, and then let's see. Yeah, this time we stop here because it's pi over 2 right there. Then we're talking about 0, 1 coordinate here. Again, our x coordinate has to do with cosine, y coordinate has to do with sine. So cosine of pi over 2 is actually 0. So you get 1 over 0 for that guy. And then cosine of pi over 2 is going to be just 1, right? Is it 1? Oh, no, sorry. Never mind. It's 0. And then over 4 pi over 2, which gives you 2 pi. Oh, so this whole thing we're saying 0 over 0 over 2 pi, so you can actually say that 0 over 0. So again, you have indeterminate form. We're like, oh, shoot. I do not have a value there. But can I find the limit value? You bet you can. We can. So what we do over here is, after we establish that it is 0 over 0, we're going to say something like this. We're going to say, let's simplify this guy. So limit up 1 over cosine of theta times cosine of theta over 4 theta as theta approaches pi over 2, right? And then, cosine of theta over, so they're reciprocal of each other, which means as long as theta is not pi over 2, it will be 1 over 1, right? So now we have a nice thing here. Limit up 1 over 4 theta as theta goes to pi over 2. And this, if you do a direct substitution, that'll be 1 over 4 times pi over 2, which will give you 1 over 2 pi. And nice. That's a number, 1 over 2 pi. So we see that the limit of this guy, this whole thing, as theta approaches pi over 2, will be 1 over 2 pi. Okay, so that is a little bit in a nutshell of how to use a trig identity to find a limit value, right? You just have to use these guys so far. Later on, you need to use a lot of different trig identity, but it's sufficient to use this one for now. Okay, number 3, again, I'm going to leave it up to you. I know I took up a lot of space. I hope that didn't confuse the heck out of you folks, but this is the work for number 1, and that's the work for number 2. And then I want to see number 3 work. If you don't have enough space, you can do it on a separate piece of paper. But try that out. So maybe tangent, you can rewrite that after you figure out that, when you do a direct substitution, since we're working on this type of problem, you're going to get 0 over 0. But check that out first. And then after that, you might have to manipulate this function. Tangent is actually equal to what? Sine over cosine. So maybe you can cancel some, like cosine over cosine maybe, right? Out, and then simplify this function into a very nice number. Okay. All right. So that concludes today's lesson for independent session, and hope you all have a great 3-day weekend. Make sure you watch this video, take notes. All you have to submit is this first page and second page. You don't have to even do this portion. We're gonna go over this on Tuesday. And you know where to submit it, right? Yep, assignment number 10 here. All right, folks. Have a good day.